Hello everyone, welcome to the OneClass channel. My name is Millan and I'm a software engineering student at Carleton University in Ottawa, Canada. Today I'll be going over a couple of physics questions at both the high school and university or college levels. If you're interested in getting help with your homework or if you're interested in getting some tutoring, check out the links in the description below. Cool, so let me switch my screen real fast and we can see the physics in action. Okay, so this is the first question that we got on the menu today. It is asking us the angle between the vector A, which is negative 25 in the I direction and 45 meters in the J direction. We have to find the angle between that vector and the positive x-axis, okay? This is a fairly straightforward question. Let's draw a diagram out to kind of represent what this question is really asking us. Okay, so let's draw out a little coordinate grid system like this. That's a pretty good straight line for freehand. So here we have our y-axis. Here we have our x-axis, and here we have our I, and here we have our j, unit direction vector. Okay, so vector A, let's say A is like an apple, so it's red. A is going negative 25 in the I direction. Okay, so suppose that we have maybe like this. Negative 25 meters in the I direction, and we have 45 meters in the J direction, which is the Y direction. And that's positive, so following this type of protocol, we have something like this, 45 meters. Okay, so this vector is going to go from the origin to here. Okay, let's call this vector A, which is negative 25 meters in the I plus 45 meters in the J direction. So the angle that we're really interested in is this angle right here. And as we can see from the diagram, we expect something that's going to be bigger than 90 degrees, but smaller than 180 degrees. Okay, so just visually from the diagram, we know what that is going to be. So one way that we can solve for this angle is with the magic of the dot product. Okay? So remember, oops, let me find my mouse real fast. So our dot product formula looks a little bit something like this. So when we have two vectors dot producted together, the result of that is the magnitude of the two vectors multiplied together, which is represented like this, and the absolute value means the magnitude of the vector. So when we have that, we multiply it by the cosine of the angle that separates them. And this is like the main dot product formula that we want to keep in mind. Now we know that A is going to be negative 25I plus 45J. And what do we want to compare? What do we want to set as our B? Well, it's saying the positive x-axis, right? So for our B, we can just do I. So this corresponds to positive x-axis vector. Okay, so when we have a system like this, you know, we're really looking for the angle between them. So if we want to isolate to the angle, then we're going to do the dot product of A and B divided by the magnitudes A, B. This will give us cos of the angle, and we just got to inverse cos both sides to get the to get the theta out of the cos. But we'll leave that in for now, just so it's going to be a little bit easier to write. Okay, so let's actually write out what this is going to be. Oops, let's put that away. Cool, so I'll write this out very formally. So here we have the vector negative 25i plus 45j dot product with just I divided by, well, the magnitude of a, we know that we have to do negative 25 squared plus 45 squared. Very Pythagoras-like. For the magnitude of b, well, that's fairly simple. It's just going to be 1 squared under the root. I'm going to write it out still just to be 1000% formal. And this is going to be equal to cos theta. Okay, so carrying on with this calculation, on the top we'll have negative 25 multiplied by 1 plus 45 multiplied by 0. Right, that's the dot product on the top. On the bottom, we will have 25 squared is 625, I believe, plus 45 squared. So this is the square root of 2650 times 1. I guess we'll write that there just to be 1000% clear. Cos theta. Okay, so on the top, as we can see fairly clearly, this is just going to be zeroed. So we don't need to worry about that anymore. Now it will just be negative 25 over the square root of 2650. And the square root of that is 51.478. And this is equal to theta if we cos inverse arc cosine like this. Okay, you kind of see how this works. To get the theta out of there, we got to inverse cos both sides. Okay, and then we shall ask the calculator to figure that out for us. So negative 25 divided by 51.478. Boom. So the result of this calculation for me is 119 degrees, approximately equal. There's a lot of decimals that I'm not going to write out because that is a lot of decimals that we need to keep in mind, but it's about 119 degrees. Yeah, that seems fairly reasonable. Like, it is between 90 and 180 as we expected. It's going to be a little bit closer to 90, which it is. It's about 30 degrees away from 90. And just visually from the diagram, we can see that it actually does look like it could fit, because it would just be 30 degrees counterclockwise from the vertical. So it does seem reasonable with respect to the diagram. So the number feels reasonable. It looks reasonable visually. We got to have the right answer. So hopefully we came to the same conclusion here. 119 degrees. That's beautiful. Cool. So, and that's the angle that it makes with the positive x-axis. That's precisely it. Okay, so that's the dot product for you. Dot product is very, very useful when you want to find the angle between multiple vectors. Okay, so yeah, this is good. Awesome. Okay, so the next question that we have on the menu today is asking us how much power must be applied to this object to accelerate it from rest to an angular speed of 3 radians per second in 7.6 seconds about the x-axis. And then it's asking us, I guess, similar questions if we wanted to get it to rotate about the y-axis and about the z-axis. Okay, so this is a very fascinating question. We have pretty much like, I don't know if you guys ever did this as young kids, but for me, like in elementary school, there was like times where we had like marshmallows and we put like toothpicks in between them. to make like structures like this, kind of like Connects toys. I'm not sure if any of y'all are familiar with that, but it's kind of similar in terms of what this is representing. We have to kind of assume something though. Assume connections are massless. The reason why we need to assume that these connections are massless is because well, we don't have any masses given associated with them, so we're gonna assume that there's zero. Like normally, like if you do have anything connected between them, it would have mass, and you do need to calculate that. But we're gonna assume that their masses are so little that we can ignore them. Otherwise, this would be impossible unless we're given them. Okay, cool. So it's asking us for the power applied. And let's represent that with the letter P. Seems reasonable, P for power. And how we want to find this is we want to take the torque that is required to get this spin to happen, multiplied by, I'm fairly certain it's the average. Yeah, it is the multiplied by the average angular velocity over the acceleration. So it's going to be torque times the average. So torque applied average angular velocity during acceleration. Okay, so how we want to accomplish this is first let's find out our W, or our, not our W, omega. Don't say W. That's a scary thing. Okay, so let's find our omega average, because we're gonna need to find that for for all three, like part A, B, C. They're all gonna need their omega average value, and it's gonna be the same for all of them because of the acceleration. But the torque is gonna be different because torque is dependent on moments of inertia. But we'll get there soon. Okay, so first, get omega average, which is needed for all and same for all. Okay, well, our average velocity is just you'd calculate the velocity, or you calculate the average velocity similar to how you calculate any other averages. So you would do omega average is equal to the starting plus the end angular velocity divided by the time. Okay, so it mentions that it starts at rest, right? So rest means it has a starting angular velocity of 0 plus from rest to an angular speed of 3 radians per second, all divided by how many seconds? It's not how many seconds. I'm tripping. That's not it. This is like the divided by 2, right? Because my bad. I was thinking about acceleration over there. Yeah, it's because we're gonna assume that it's like a constant acceleration. Acceleration. Okay, so you know, this is a fairly straightforward calculation. So we know that our omega average has to be 1.5 radians per second. That's going to be important. Okay, so let's square that off. Now we need to find torque in x-axis rotation. Okay, so what I mean by x-axis rotation is like, if the x-axis was like the axle of our of a wheel, that's what we would be doing. So what we need to do here is we know that torque is going to be equal to the angular acceleration multiplied by the moment of inertia, right? So the torque in the x component, in the about the x-axis rather, is going to be equal to the moment of inertia about the x-axis multiplied by the angular acceleration about the x-axis. But angular acceleration is going to be the same for everyone. Okay, so let's find our angular acceleration first, because that's what is easier. So we know that our moment of inertia, we'll keep that as like that for now. But for our angular acceleration, we know that this has to be the change in velocity with respect to time. So this will be angular final minus angular initial over the time. Okay, and that, hopefully is fairly clear on how that corresponds to angular acceleration. Now for the moment of inertia, moment of inertia is like how difficult it is to rotate this stuff, and or this. So you see how if we're rotating about the x-axis, it's really only the 3 kilogram and the 4 kilogram up here that are going to contribute to the to causing difficulty in rotating here. Because if we're going to assume that the 2.5 and the 1.2 down here, if we assume that those are like perfectly on the line of the x-axis and they don't protrude outwards at all, they're not going to cause any increase to the moments of inertia of the system. Okay, so it's only going to be the 3 and the 4 kilograms that are relevant to this, and we know that the equation for moments of inertia is the sum of all masses with multiplied by the distance that they are, the perpendicular distance that they are away from the axis of rotation. Okay, so in this case, we're given it as 0.5 meters. Okay, so we can sub that into here. Oops, it's r squared. My bad. Okay, so we can send that into the equation here. Is equal to the mass times the distance, the perpendicular distance away, multiplied by final minus initial over time. And we know that yeah, we just need to find this and we'll be good. Okay, so when we scroll back up to here, we know that we only have 2 particles or 2 points that are on this system that are relevant to the moment of inertia. In this case, the 3 and the 4 kilogram. So we shall do this. So the 3 kilogram is 0.5 meters away, meters squared, plus we have the 4 kilogram over there, which is also 0.5, whoops, not 0.5, 0.5 meters squared away. And then our final angular velocity is 3 radians per second minus our initial, which was, well, 0 because we started at rest. And it's all divided by the time that it the time that it took us to change that angular velocity, which in this case 7.6 seconds. Okay, so our torque about the x-axis is going to be the results of this calculation. So 3 times 0.25, because 0.25 is 0.5 squared, plus 4 times 0.25 times 3 divided by 7.6 is equal to, my calculation is, 0.6908 Newton meters. Yeah. Okay, but that is not what we need. We need to get the power, right? And the power is just the torque multiplied by the average angular velocity. We know that the average angular velocity is 1.5 meters. So power for the x direction is going to be the torque in the x multiplied by the average angular velocity. So we know the torque is 0.6908 Newton meters multiplied by omega average, which we know is 1.5 radians per second. Okay, so let's multiply them together times 1.5, and I got our power in the x direction is going to be 1.036 watts. Okay, hopefully that's the same calculation we got here. Yeah, just with a little bit of rounding, but yeah, precisely. So that's in the x direction. Now in the y direction, it's going to be quite the same. So let's actually write it out like the full equation like this, and then we can see what we can sub in, and it'll be a lot easier. So now the y direction, or the y-axis. So we know that this is going to be equal to the torque in the y multiplied by omega average. And we know that the torque in the y is going to be the moment of inertia in the y multiplied by the angular acceleration multiplied by omega average. These will be the same, as x-axis. All we have now is just we need to look at who is going to have a contribution of inertia to about if we're spinning about the y-axis. So it's going to be the same equation, mr squared, all in brackets, multiplied by angular acceleration and w average. Okay, so let's take a look at our diagram here, and we'll see if we're spinning about the y-axis, kind of like if we're you know, it's like a flag, kind of like a flag. We can see that we have the 4 kilogram, which is we have the 4 kilogram and the 1.2 kilogram that are going to be relevant to this moment of inertia calculation. The other two, since they're on the y-axis directly, they will not contribute to the moment. Okay, so let's write this out. Py, power of y. So our first mass is going to be the 4 kilogram. 4 kilogram multiplied by 0.7 meters, but we got to square the distance, plus our second mass, 1.2 kilograms, multiplied by 0.7 meters squared again. And our calculation for alpha is what was it? It was 3 over 7.6. So 3 radians per second over 7.6 seconds. And our omega average was 1.5 radians per second. Okay, let's ask our handy dandy calculator to figure this out for us. So we got 4 times 0.7 squared plus 1.2 times 0.7 squared, close that bracket, times 3 over 7.6 times 1.5. So my power in the y direction is hopefully gonna agree with this. Yeah, exactly. So my py calculation is 1.509 watts. Awesome. Now we want to follow a similar procedure for the z direction. Now the z direction, we don't see it on here, but assume a right hand rule. So z axis assuming right hand rule pointing out of page. Okay, so right hand rule, our pointing index fingers are going to go along the x-axis, our fingers are going to curl, or our palm is going up towards that y direction. Our thumb is telling us where the z direction is, and the z is, well, pointing right at my face. Okay, so it's kind of like, you know, if you're holding your arm out and you're imagining things orbiting around your hand like this. That's pretty much what we want to imagine here. So PZ is going to follow a similar system. So we have to find the torque in the z direction multiplied by our omega average. And we know that our torque in the z direction is going to be equal to our moment of inertia in the z direction multiplied by angular acceleration, which is the same, and multiplied by our angular velocity average, which is the same. And you know, it might look repetitive, but I just want to be 1000% clear that it really is a very similar thing that we're doing over and over again. And we should expect a different result on this. So when we think about if we're rotating about the z-axis, we know that, in fact, all of these, except for the 2.5, the 2.5 is the only one that's not going to be relevant to the measurement of the moment of inertia about the z-axis, because this is the only one. The 2.5 is the only one. Excuse me. The 2.5 is the only one that is actually physically on the z-axis. So it's only things that are not along the z-axis that are going to be relevant to this, okay? But keep in mind, we're going to need to do a little bit of Pythagoras math to get the 4, but we'll get there when we get there. Okay, so let's write this out in full. Power in the z. We will first need to do, let's first talk about our 3 kilogram one. So that's going to be 3 kilograms multiplied by 0.5 meters squared plus, now this one, we need to be a little bit Pythagoras to find it, because we're looking for the distance from like corner to corner on, oh, you can't see my cursor, like this corner to corner type distance. That's the distance we're looking for this one. Okay, so that one is 4.0 kilograms, 4 kilograms. Now, since we're doing like a Pythagoras theorem thing, it's going to be 0.7 squared plus 0.5 squared, all under the root. 0.7 meters squared plus 0.5 meters squared under the root. But that root really is not too relevant because of, we have to square it. but we'll write it out just to be 1000% complete. And then our last weight that's going to be relevant here is going to be the 1.2 kilogram. And that's going to be multiplied by fairly straightforward 0.7 meters squared. And this whole thing is multiplied by, well, it's going to be the angular acceleration, which is still going to be 3 radians per second over 7.6 seconds, multiplied by 1.5 radians per second. I believe, yep, exactly. Okay, so power about the z-axis to cause this rotation. Let's math this out. So the first term, 3 times 0.5 squared plus, now this is the spicy one, 4 times, in brackets, is going to be 0.7 squared plus 0.5 squared, but we don't need to put that under the root because the square root and the squared neutralize each other. And then we're going to add plus 1.2 times 0.7 squared. And this times 3 times 1.5 divide 7.6. And my result for this is 2.54. And hopefully we have a similar calculation here. Oops. Wait a minute. Something in the math is not agreeing with my calculation and the calculation here. 4.0. Okay, so I trust my answer more because I can see in my calculator that everything's lined up. Nothing to be worried about. It's just a minor calculation error. So my results for this power calculation is going to be 2.4, whoops, not 4, 2.545 watts. Okay, the only thing that's concerning is this calculation right here, but otherwise everything appears to be good. Yeah. Awesome. So that concludes this question. Pretty fun. Pretty exciting stuff if you ask me. For z-axis. Yeah. Okay, so this is the next question that we got on the menu today. It is asking us, a generator uses a coil which has 160 turns and operates in a 0.5 Tesla magnetic field. The frequency of this generator is 60 Hertz, and its electromagnetic field, electromotive force, has an RMS value of 120 volts. Okay, so its voltage, basically it's saying its voltage is RMS 120. Assuming that each turn of the coil is a square, okay, that's pretty important. Determine the length of the wire from which the coil is made. Okay, so let's extract the information of interest out of this question. Okay, so of interest. So the first thing that we are given is 160 turns. So that's going to be our n value. 160 turns. And our magnetic field is represented with B. That is 0.5 Teslas. Okay. The frequency is 60 hertz. 60.0 hertz. And its voltage, or let's just call that EMF. This is equal to 120 volts RMS volts. And something of interest about these turns is that assume each turn is a square. And that is definitely a square. That's not a rectangle. Don't worry about that. Okay, so we have to determine the length of the wire. Now to do that, we need to get our equation that is going to be corresponding to this. So the equation that we want to use is this one right here. This is a pretty common Coil equation that is commonly used. So our here is our epsilon, or our EMF, is equal to our number of turns times the area times our magnetic field times our angular frequency. Okay, so angular frequency, B comes from here, N comes from here, and this is cross-sectional area of coil. Okay, and an EMF, well, that's pretty straightforward. But we don't really know the area, but we know that the area is going to be square, right? So cross-sectional area of the coil has to be a square. And let's say area is equal to its side length squared. And that makes perfect sense because we know that it's a square. That means all side lengths have to be the same. And well, the area of a square, length times height, even though they're the same, is just L squared. Okay, so we could rewrite this as, let's just say that this is equal to V. Just so it's a little bit easier to write. So we have V equals N. Instead of A, we'll have L squared. B, and instead of angular frequency, this will be 2 pi F is equal to omega. So we can just do 2 pi times the frequency we gave us, because the frequency that we were given is in hertz. So we need to convert that to radians per second. We just multiply 2 pi to that. Fairly straightforward. Okay, now we are trying to find the length of the wire, and which means that we're trying to isolate L. L is just the side length, but the total length of the wire, well, we'll see how we proceed with that. Think about it for a second. Okay, so isolate L, because everything else is given to us. So we'll have V over NB 2 pi frequency is equal to L, and we have to square root the left side because the right side would have had L squared before we did that. Okay, so we can possibly sub in our numbers. So we get a similar looking thing here. Another thing that we need to mention is this is for the peak. Yikes. Peak voltage. We know that V peak is equal to root 2, which is about 1.4 times V RMS. Okay, so yeah, that's my bad. I'll make a correction real fast. So this will be so root 2 RMS and then a root 2 term. Okay, and just to go back up here, just to make things super clear, peak voltage. Okay, so now everything should be in order. Okay, so yeah, so now we have our isolation for this. Now we can sub in our numbers to get our L. So our RMS value was given as 120 volts. So we have root 2, 120 volts, N was 160 turns, B is 0.5 Teslas, 2 and pi, well, those are just numbers, and our frequency was given as 60 Hertz. Okay, so let's run this through our calculator. So square root of 2 times 120 divided by 160 times 0.5 times 2 times pi times 60, close the bracket, and then put that whole thing to the square root. And my calculation for that L is 0.075 meters. So what we got here, .075 meters. Awesome. Okay, so this is the side length of one, or the side length of one turn of the coil. The total length of the coil, as we can see here, is like actually, I think I have a pretty good model here, because I actually do have some real life wires and kind of show what's going on here. So make my camera a little big for a second. Okay, so here, you know, it's a fairly straightforward blue wire. Hopefully you can kind of see it well. But as we make it a coil, we're kind of making it into something like this. Okay, so you can see like this is camera focus, please. But you can see like this, we only found, like if this was a square, we only found this here. But the total length of the wire, you recognize that, well, the entire area, if we only know the length, we know that one loop is going to have 4 times that, assuming it's a square. These things don't tend to want to be squares. But yeah, one side is going to, one coil, one turn is going to be 4 times the side length. And we have, well, we have a lot of turns, 160 of them. So that, we'll have to multiply that to get the total length of the coil. Okay. So L total is equal to 4 times L times N. So these 2 terms are going to be 1 turn. And this is just number of turns. So L total is going to be 4 times L, which is 0.075 meters, multiplied by 160 turns. And this is going to be something that I asked my calculator, times 4 times 160 And I get 48 meters. Is that what we got here? Yeah, so okay, so this is the total wire length. And this is a fairly reasonable answer. Like 48 meters, that's, you know, it might take you like 5 or 6 seconds to sprint that at full speed, but it is reasonable to see a coil that long because they are really rolled up 160 times. It's like kind of how people say every vein in your body laid end to end could go around the earth a couple times. Like when you really roll these things up, they really do get a lot smaller in size, and they can get pretty long, even if the coil is like only 7 centimeters per each side. Overall, it can be 48 meters, which is fairly large, but reasonable. Okay, so this above solution is actually very good, and that's awesome. Cool. Awesome. Beautiful. Okay, so this is the next question that we have on the menu today. It is asking us, a trunk with a mass of 23 kilograms is on the floor. The trunk has a very small initial speed. The acceleration of gravity is 9.8 meters per second. So we're on Earth here. That's nice to know. What constant horizontal force pushing the trunk is required to give it a velocity of 10 meters per second in 20 seconds if the coefficient of sliding friction between the trunk and the floor is 0.63? Okay, so let's actually draw a diagram of what is going on in this situation, and then from that diagram we can make some mathematical moves to do exactly what we need to do. Okay, so we have a mass here, and we know that that mass 23 kilogram. 23 kilogram. Let's draw it as a box. And we are on a fairly smooth ground where the coefficient of kinetic friction, which is when it's in motion, and that is 0.63. Okay, so let's consider the forces that are going to be in this situation. We know that we have gravity because, well, it's not floating away in space, so we definitely got gravity. So that's Fg, and that's going to be equal to mass times gravity, equal to 23 kilogram multiplied by 9.8 meters per second squared. Okay, and that's going to be our Fg, and we're also going to have a normal force. I'll draw it in blue so it's a little bit more clear. Now, the reason we have a normal force is because, well, the trunk is not sinking through the ground. Okay, so the ground itself is providing a force that counteracts the gravity, and in this case, it's just going to be equal to Fg. Equal because no sinking into ground. Okay, fairly straightforward. Now it says that we have a horizontal pushing force. We're going to need to solve for that, but we're going to draw that in. It just is unknown. So let's call that Fp for F push. Fp, solve. And we have a pulling force, which is actually just the frictional force. And our frictional force is going to be our coefficient of friction. So mu k multiplied by Fn. And since we know that mu k, Fn has to be equal to Fg, we could also write this as mu k times mass times gravity. Okay, so we need to know what the net force is, and we can have the net force on this. And if we define our axes like this, x, y. I know you may not be used to seeing the x going towards the left, but you know, you can set the coordinates however you please. we know that the sum of the forces in the y direction has to be 0, and that there has to be a net force in the x direction. Net force purely in x direction. Okay, and our force has to must accelerate from, okay, so notice how it says has a very small initial speed. We're going to treat that as 0. Now, the reason why it's not saying the trunk starts at rest is because then we would have a coefficient of static friction. Now, since they gave us a coefficient of sliding friction, they have to say that it has like a non-zero initial speed. Otherwise, we'd be going with static friction, and that it would not be harder. It would be a little bit harder, but that's not something that we really need to worry about right now. So it must accelerate from 0 meters per second to 10 meters per second in 20 seconds. Yeah. Okay. So the acceleration that we're going to need is as follows. So we know that our acceleration is going to be our v final minus our v initial over the time that it takes for that change to happen. I believe that's how it's calculated here. Yep. Okay. So our initial is going to be 0. Our final is going to be 10. So here we're going to have 10 meters per second minus 0 meters per second, all divided by 20 seconds. And quick with the maths, we can see that this is 0.5 meters per second squared. Okay, so given this, this is in the x direction, and this will be going towards the left with respect to our diagram here. So we know that the forces in the y direction have to be 0, but we know we should instead find the sum of all our forces in the x direction and equate them to our mass multiplied by this acceleration. Okay, so forces in x direction is equal to their mass times our acceleration in the x direction. So we're going to have our FP, which we're trying to solve for. And this is positive because this is going towards the left in this case. So you can draw a little symbol like this, an arrow pointing towards the left with a plus to show that this is our plus direction. We could have easily put the x direction in towards the right, but it's good to be familiar with different types of coordinate systems. And we have to subtract our friction force because that's going the opposite direction. So first I'll write it as minus F. And we want to isolate that, right? FP is what we're trying to solve for. That is the main goal of the question. So to isolate this, we can see that FP is equal to negative F. Wait, never mind. It's not. It's going to be we bring that FF, the friction force, to the other side. So we'd have MA in the x direction plus the frictional force. Okay, so FP, as we're trying to solve for, our mass, it was given to us in the question, 23 kilograms. Acceleration in the x direction, we know that has to be 0.5 meters per second. We calculated that this way, and that was given to us. That originally came from, the velocities that we're eventually going to need to reach. So that's 0.5 meters per second squared plus the frictional force. Now from our diagram up here, we know that our frictional force is dependent on our normal force. We know our normal force is equal to our gravitational force. Okay, so we know that we have mu k, coefficient of static friction times mass times gravity. So our coefficient is 0.63 times our mass, 23 kilogram, times 9.8 meters per second squared. And that's our G. Okay, so once we find this calculation, this will be our force of our push required for this to happen, and that will be that. So we got 23 times 0.5 plus 0.63 times 23 times 9.8. And my result for this, 153.5 newtons. Okay, hopefully we have a similar calculation here. Yeah, just with some rounding stuff. We were only given two significant figures, so to adjust for that, we should write instead Fp is equal to 1.5 times 10 to the 2 newtons, just to be a little bit more formal with our significant figures incorporated in here. Okay, so yeah, that is the solution. We just gotta balance the forces and get these dynamics equations. Setting up these dynamics equations of like the sum of all forces is very, very important and quite often used, especially in like mechanical engineering or people who are into more of like architecture, that type of stuff. Stuff is very useful, but very cool. And this solution is good. Is good. Awesome. Okay, so the next question that we have on the menu today is asking us, well, we have 2 point charges, one that's 30 nanocoulombs, one that's negative 40 nanocoulombs, and they're both held on the x-axis, with the 30 being at the origin and the negative 40 being at 65 centimeters along. A particle with a charge of 42 microcoulombs is released from rest at 28 centimeters. If the initial acceleration of the particle is 135 kilometers per second squared, what is a particle's mass? Okay, this is a very fascinating question. I actually very like this question. As we should start this off, as we should start in many situations, we want to have a diagram to kind of give ourselves like a visual representation of what is going on in this question. Okay, so here we have x equals 0. Let's just get our locations of interest at first. And then we have 65 centimeters as a location of interest. This is absolutely not to scale, but it's not that important. So 0.65 meters is another way to write that out. In my opinion, it's a little bit safer to write our distances in base SI, so convert your centimeters into regular meters. And we know that our other location of interest is 28 centimeters. That's about halfway, slightly closer to the 0. So let's call that 0.28 meters. Okay, and here we have a charge. Let's call this Q left, QL for Q left. And that is 30 times 10 to the negative 9 coulombs. 10 to the negative 9 is the same as nanocoulombs. Here, let's call this QR because it's to the right of us, or to the right of the thing of interest. And this is negative 40 times 10 to the negative 9 coulombs. And in the middle, we have a particle, and let's call this QM for Q middle. This could be, it's given by the question is 42 times 10 to the negative 6 coulombs. Okay, the reason I did negative 6 instead of negative 9 for the power is because, well, we have microcoulombs instead of nanocoulombs. Okay, so that's a big difference maker. And we know that it has an initial velocity or an initial acceleration of 135 kilometers per hour. So acceleration is equal to 135 kilometers per second squared, which is equal to 135 times 10 to the 3 meters per second squared. And since it's positive, it's going to be going in the positive x direction. That means towards the right, which makes sense because we know that the left charge and the middle charge have the same sign, so they're going to try to get away from each other. Assuming QL is fixed, that means QM is going towards the right, and it's getting attracted to the right as well. So, you know, that's the only way that it could work. So, pretty much what's going on here is, let's color code these. So if this one is that color, like pinkish, this has to be applying a force this way, so repulsive force. And maybe if we have a different color, maybe like blue, this one is going to have a force this way. Attractive force. And that is purely and only because of the signs, okay? And opposites attract, like same sign, get away from each other, okay? So it's a nice, easy way to remember this. So we know that our force net, our F net, is equal to our mass times acceleration. Acceleration, well, we just calculated, or I mean, it's given as this. This is what we're trying to solve for. And we know that our net force is going to be equal to our force contributions from both of these the 2 points, individually. Okay, so to represent that, we can call that FL plus FR. So the forces as caused by the left charge and the right charge. Okay, so we know that the electric force, let's do this a different color, maybe green. So the electric force equation we know is KQQ over R squared. K is 9 times 10 to the 9. Q and Q are charges. And R is distance of separation. Okay, so this is going to, this equation is what we're going to use for both of the FL and the FR. So let's sub that in and see what it looks like. So instead of writing F net, I'll just write MA because we know that they have to be the same. And here it's going to be K QL QM over, now it's going to be the separation distance between them. It's going to just be 28. That's the separation distance between QL and QM. So it's 28 minus 0, fairly straight forward. 0.28 meters. We got to square that, don't forget it. Plus K QR QM. And we have to find the distance of separation between 28 centimeters and 65 centimeters. So that is 37, I believe. I'm just gonna double check that because I can't always trust my math. 37 plus 28, 65. Okay, so that will be 0.37 meters on the bottom. meters squared. And what we can do here is, since we're trying to isolate this, we can also factor out the K and QM. Factor out QM and K because they're the same. So here, to isolate that, we'll have, whoops, we're not isolating A, we're isolating M. We are going to have K and QM factored out. A, when we isolated M, well, we just divide both sides by A. And then here we're going to have QL over 0.28 meters squared plus QR over 0.37 meters squared. Okay, so subbing in the numbers, we get 9 times 10 to the 9. That's our K value. Our QM, so that's our middle charge. That's going to be 42 microcoulombs. 42 times 10 to the negative 6 all over our acceleration, and our acceleration is 135 times 10 to the 3 meters per second squared. I'm not going to write the units because, well, it gets quite long. Our left charge is 30 times 10 to the negative 9 over 0.28 squared plus our QR. Now our QR is originally given as negative 40, but since we have our directions in here, we're just looking for the magnitude, so I'm going to put in a positive value, not because this is a positive charge, just because we already had the signs incorporated into the diagram, so we're not going to incorporate them into our calculation here. Okay, so it's going to be plus 40 times 10 to the negative 9 over 0.37 meters squared. Okay, so let's calculate this out. Asking my handy dandy calculator. 9 times 10 to the 9 times 42 times 10 to the power negative 6 divided by 135 times 10 to the 3 multiplied by 30 times 10 to the power of negative 9 times 0.28 to the power of negative 2 plus 40 times 10 to the power of negative 9 times 0.37 to the power of negative 2 and my result for this calculation is in the microgram scale. Yeah, exactly. So my mass here is calculated to be pretty much the same value. So I got 1.8894954 times 10 to the negative 6 kilograms. And from our original question, these have one significant figures. So our final answer is going to need to be one significant figure. One sig fig. So our m will just be 2 times 10 to the negative 6 kilograms. Another way that we could say this is 2 milligrams. Okay, because 10 to the negative 6 times 10 to the 3 is 10 to the negative 3, because the kilo turns into 10 to the 3, so it becomes 2 milligrams. Okay, so this is the mass of particle. Happy face. Okay, so our calculation here is good, and this solution is good. So wasn't this a fun time? Once you, the hard part is really doing the algebra. Once you do the algebra good, it's just ask your calculator, and that's fairly straightforward. So yeah, just start off with the diagram. Once you got the diagram, everything else should be smooth sailing. Smooth sailing. Okay, cool. So this solution is good. Is good. Oh man, that was the last question. Ain't that unfortunate? Time flies when you're having fun. So those are all the questions that we had for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you would like to submit your own questions, we have video links in the description where we can help you accommodate that. Remember to leave a like and a comment if you enjoyed the video, and if you really enjoyed the video, share it with your friends. This has been Millan from OneClass. I hope today was a fun physics time, and I hope you have an amazing day or an amazing evening, depending on what time you're watching this. And remember, physics is always a good time. Always trust the physics, and the physics will trust you too. Okay, take care and stay safe.